Hi, I'm Hyun Kook Lee from the APL of the University of Huddersfield. In my part of this session, I'm going to introduce different types of 3D microphone arrays designed for music and soundscape recordings with discussions on relevant psychoacoustic principles. I've also got some binaural audio samples to play from the 3D Marco recording database to demonstrate perceptual differences between different types of 3D arrays. And I will also play some of my 3D choral and soundscape recordings I've recently made using my own techniques called PCMA3D and ESMA3D. So let's start with the categorization of 3D microphone arrays. The scope of this talk is limited to techniques for music and ambience recording, and it doesn't include arrays designed purely for sound localization or beamforming purposes. In terms of physical configuration, we can broadly split the existing 3D arrays into three groups: horizontally and vertically spaced, and horizontally spaced and vertically constant arrays, and horizontally and vertically constant arrays. So we can call the first group HVS arrays in short, and the second group HSVC, and the third group HVC in short. So the HVS arrays apply a certain spacing between all microphones, producing interchannel time differences vertically as well as horizontally. It's well known that a wider horizontal mic spacing would lead to a stronger spatial impression in reproduction due to a greater amount of interchannel decorrelation. And this is one of the main reasons why a spaced microphone array is often chosen by professional engineers. But recent research found that vertical microphone spacing and vertical decorrelation tend to have a minimal effect on perceived spatial impression in 3D sound reproduction. Based on this, some 3D microphone arrays like PCMA3D or OLTF3D have been designed using the HSVC concept, where the middle and upper layers have no spacing, while horizontally arranged microphones are spaced for producing spacious images. We'll look into this principle a bit more later. Both the HVS and HSVC arrays can be described as perceptually motivated arrays because their common aim is to achieve certain perceptual characteristics in phantom image localization and spatial impression by manipulating the interchannel relationships between the microphone signals. So the main motivation here is to provide the listener with a spatially and tonally pleasing oral experience while plausibly representing the sound field rather than duplicating it in reproduction. On the other hand, arrays in the HVC group have no or minimal spacing between all microphones, thus relying on the interchannel level difference cue for directional source imaging. And they are typically designed to utilize the ambisonics technology. And these arrays can be described as physically motivated arrays, as the design goal is to physically reconstruct the sound field as accurately as possible in reproduction. And there are a number of commercial first order and high order ambisonic microphones available these days. And also there are several native techniques to record for first order ambisonics. But in this talk, I will be just focusing on the HVS and HSVC arrays. As mentioned earlier, the HVS arrays basically aim to produce sufficient decorrelation between microphones, both horizontally and vertically. And the low frequency decorrelation is known to be important for providing the sense of listener envelopment and a large sweet spot. And the low frequency decorrelation is achieved by increasing the mic spacing. Basically, as the mic spacing becomes wider, you can achieve a full decorrelation to a lower frequency. For example, as you see in these graphs, based on the diffuse field coherence theory, we can calculate that with a 1 meter spacing between two omni microphones, you can get a near zero correlation between signals at about 200 Hz and frequencies above that. But if the spacing is decreased to about 0.3 meter, then the lowest frequency where a similar amount of decorrelation is achieved is raised to 500 Hz. 2L Cube and OCT3D are good examples of HEVS arrays as they are distinctly different in design concept and also in the actual perceived characteristics. 2L Cube is a technique devised by Morten Lindberg, and the array employs 9 Omni microphones arranged in a cube layout with 1 meter dimensions. On the other hand, OCT3D by Gunther Tyler and Helmut Wittek uses directional microphones for all channels, and it augments OCT surround 5-channel microphone array with 4 supercardioid microphones facing upwards and placed 1 meter above the main layer. The OCT is optimized for reducing horizontal interchannel crosstalk between the horizontal microphones, and the upward-facing supercardioids also aim to suppress the interchannel crosstalk occurring vertically. So there is this question of which of these different polar patterns of height microphones would be more suitable for creating the sense of height in reproduction. Firstly, Omni microphones are often preferred by professional engineers because they offer more extended low end in the frequency spectrum. But one of the potential issues is that Omnis capture sound from all directions, which means Omni height would likely capture a lot of direct sound as well as ambience, and the direct sound present in the height channels can be regarded as crosstalk in terms of vertical localization, which causes the perceived source images to be localized in an elevated position. So in order to locate the source image at the height of the main speaker layer, the vertical interchannel crosstalk needs to be suppressed by at least 7 dB for vertically spaced microphones. And this can be simply achieved by using cardioid or supercardioid height microphones angled upwards so that you can achieve this 7 dB difference between the main microphone signal and the height microphone signal. So in this case, the height microphone is focusing more on the ambience, and the main microphone is focusing mainly on capturing the direct sound. We also found that the effect of vertical microphone spacing on spatial impression was not significant for musical recordings from an experiment with 4 different vertical microphone layer spacings of 0 to 1.5 meters. This result implies that the main and height microphones can be configured in a vertically constant way, ensuring that there is enough channel separation between the microphones. So the main microphone mainly captures the source, while the height microphone focuses on capturing the ambience, but they can configure it in a vertically constant way, which also has a benefit in terms of down mixing, because when you combine the signals, there is no phase cancellation. In the case of vertical constant configuration, like PCMA3D, the necessary amount of crosstalk suppression is 9.5 dB, according to the experimental result we obtained. Again, we can achieve this simply by pointing the supercardioid or cardioid microphones directly towards the ceiling. And Sharp's OLTF3D and my ESMA3D microphone arrays, designed for capturing outdoor ambience in 3D, also share the same horizontally spaced and vertically constant design concept. So now I'd like to demonstrate perceptual differences among the 3 arrays I introduced earlier, which are 2L Cube, OCT3D, and PCMA3D. The recordings I'm going to play are from the 3D Marco database, which I produced last year. The database includes various musical recordings made in a concert hall using 71 microphones simultaneously. The database is being widely used in various areas such as spatial audio research, spatial ear training, acoustic analysis, and virtual 3D recordings using impulse responses. And it's available for free download from this link here. And the list of the microphone arrays included in the database is shown in this slide. But due to the time constraint in this session, we'll be comparing just the 3 arrays, PCMA3D, OCT3D, and 2L Cube, which demonstrate distinct differences in spatial and tonal characteristics. Okay, so for this demo, I prepared these short binaural audio samples To create the samples, the original 9-channel signals for each microphone array was binaurally synthesized using the KU100 HRIRs corresponding to the last picker positions in a 9-channel layout, which was basically the 5.1 setup with 4 height speakers raised at 45 degrees above the main layer speakers. All of the microphones used for these recordings were the DPA-D Decade series, so 4006 for omnis and 4011s for cardioids and 4018s for supercardioids. I'm going to play each recording a couple of times, switching between each microarray, so please listen for differences in terms of tonal attributes as well as spatial attributes such as image localizability, vertical image extension, perceived depth, and listener envelopment. Okay, so I understand it may be difficult to hear all the differences from this quick comparison over headphones, and I strongly encourage you to download the samples from the link below and compare them against yourself, even better if you have a 9.1 playback system. But from my observations, each of these three arrays has a certain merit over the others. To me, OCT3D has a slightly greater depth and better distance perception compared to the others, especially for the piano recording. And 12 Cube has a slightly warmer tone and a better low frequency response, especially for the cello in the string quartet recording. But it may sound slightly phasey for the quartet and slightly muddy for the piano. This may be because all of the 9-channel signals have direct sounds, and when there are some dead ears with different time differences, it can cause the comb filter effect. The PCMA3D to me has a better clarity than the other arrays, and it has a good width and openness to the sound, but it may seem a bit closer to the head than the OCT3D and slightly lacks the low end energy compared to the 12 Cube. Now let's have a listen to the organ recording. So I guess you found the difference quite obvious with this organ recording. The 12 cube has a more extended low-end response compared with the other arrays, whereas PCMA3D or OCT3D seems to have a slightly better clarity in the upper mid and high frequency regions. The better low-end response with the 12 cube is the result of using Omni microphones, but the upper mid-range clarity may be a limitation due to the confiltering. The directional microphones have less interchannel crosstalk, so it has a better clarity, but due to the mechanical limitation of directional microphones, they don't tend to um, provide the sub frequencies of this large instrument. So if you want to compensate for the low end response when using directional microphones, additional omni microphones can be placed right next to the directional microphones, and only the low frequencies of those omnis can be mixed with the directional microphone signals to extend the low end response. And this is the so-called Strauss packet technique. So I'll demonstrate the effect of adding the low-pass omni signals to PCMA3D. So in this example, I took the omnis from the 12 cube, the main layer of the 12 cube, and low-passed the signals below 150 Hz. Lastly, I'd like to demonstrate the differences in the imaging of a single trumpet source, which was located at plus 45 degrees in the right-hand side of the microphone arrays. Please listen for how stable the perceived source image position is. You may find, depending on the note, the image position moves between left and right. So finally, I'd like to play some choral recordings I made using the PCMA3D microphone technique, and also some of the New York soundscapes captured using the ESMA3D microarray. These recordings were binaurally synthesized with a virtual acoustic simulation of the APL listening room.
Attention customers. For your safety and the safety of others, please do not sit on the floor or stairs in Grand Central Terminal. Thank you for your cooperation.